So I'm going to try to leave like probably about 5-10 minutes for Q&A. Hopefully will be a lively conversation. But what I want to talk about today is a lot of people out there talk about explainable AI. I'm going to talk about something that beyond explainability, something that how put the spotlight on explainable AI and some of the deficiency and how should we approach it and etc. So I hope it will be a lively discussion. But let me start with a few topics that I'm going to try to cover quickly. So one probably will be covered deeper than the other, but talk about quickly the application of machine learning in banking. Talk about explainable AI in general, and then we're going to talk about beyond explainability. We're going to talk in particular inherently interpretable machine learning, something that very, very crucial in highly regulated industry like banking, particularly for those application that really high risk application or important application that impact people's livelihood. As part of that, we're going to look at, we talk about deep neural networks, so we can make deep ReLU network as interpretable model as well. So when I talk about interpretable model, it's not only simple traditional statistical model. You will see in my presentation today, it will be sophisticated deep learning model. You can make it inherently interpretable. And what I mean by inherently interpretable, we're going to look into that. All right. So first is the if you look at the broadly application of AI ML in banking are really in two main categories. One is in the area of predictive analytics. This is typically dealing with structured or tabular data. This is more traditional application in banking. Banking is always very, very data rich. It's always data driven. We move information. So that's why it's very natural for banking to be adopting AI and ML. We have a lot of in this application for predictive analytics. We have a lot of existing practice in banking for many, many years. We have business process infrastructure to support it. So typically application of AI and ML in this space is not a technology project anymore, but it's really talking about deployment on the existing infrastructure, etc. Credit risk, marketing, fraud, anti-money laundering, and on and on. So those are examples where traditionally we use statistical model. Now you can use machine learning, and it's broadly applied across the board. The second category are really more in the process automation. This typically dealing with unstructured data. Banking is very, very process heavy. So it lends itself for a lot of automation, a lot of information movement, etc. So that's it's very ripe for automation. When we're dealing with this space, are typically a lot of new area dealing with compliance, dealing with conduct surveillance. I'll give you a few examples. Customer support, like complaint handling. When people make a phone call. What would like to get replacement of credit card, whether the call is fraudulent or not, etc. Those are the call are listened by machine learning and helping the person that help on the other side answering the phone. A lot of document capture and classification, tons of document. So processing, for example, during LIBOR transition that we just had, is searching for all documents that touch LIBOR so that they can be converted into new rates. So that's all kind of things that that's typical in banking are really in those two areas. Now, when we start talking about using machine learning, using AI, they are machine learning and AI are models. And in banking, we have very disciplined model risk management to manage our machine learning and AI. Some of you probably, actually National Institute of Standards, NIST, just published yesterday or 2 days ago, their framework guidance on the model risk management. So they are following the footstep of financial industry. to really encourage people to practice model risk management. So in model risk, we all believe that all models are wrong. And when they are wrong, they create harms. They create unintended consequence. It can harm the company. It can harm the user. It can harm people that subjected to model. So that's with that where is the source of that? Where is where it can happen? It can happen during model design. It can happen also when the model probably all right, but improper model use. So that's the type of things that we need to think about. Every model will be wrong, and they can create unintended consequence and harm. If it's financial model, it can create financial harm. If it's a compliance model, it can create compliance against law. It can create reputation. So I just put a few examples here in terms of AI problem, a machine learning problem. It's never short any of problem. Every day we encounter this in the news. So it's something that we need to think about when we're doing AI, be it for automation. You can always think about what can go wrong. How is this wrong? How is this impact to the downstream process or the upstream process or whatever it is. So always think about what can go wrong, and because things will go wrong. There are various things that can make it wrong. I'm going to focus on one area only today. This can be a discussion. A lot of each of the topic and itself can be a lengthy discussion. But I'm going to talk about the issue of transparency, particularly interpretability, model interpretability, because this is very, very important. And especially when we have human in the loop, the interpretability are very important, because when model wrongs, people need to be able to do what can we do with that. Flying blind without knowing what can we do, people typically make situation worse. People are very noisy. The decisions are very noisy. Without the proper information, typically, most of the time, people will make situation worse. So transparency, interpretability are so important. So we're going to focus on this in today's talk. Let me talk about explainable AI. When people talk about explainable machine learning, explainable AI, it really is coming into two main areas. One is model that intrinsically interpretable. The other one is, the second one at the bottom is really what we call post-hoc explainability. You applying tool to explain what the AI, what the machine learning does. Unfortunately, they call it explainable AI. So the AI, the machine learning itself is not explainable. You try to explain it, and you call it explainable AI. Unfortunately, that's the case today. So you see, you heard a lot about global explanation, local explanation, or people use simplified or surrogate model. The alphabet soup in this area. People talk about variable importance, talking about PDP, people talk about line, people talk about SHAP. So a lot of tools that trying to explain a machine learning. And then they call all this collection as explainable AI. I think it's misnomer, in my opinion. They are not explainable AI. They try to explain AI. And when you try to explain it, the explainer is a simplification. It itself is a model. It itself can be wrong. And we'll go to some example later. On the other hand, on the intrinsically interpretable model, that's the top. We know some of the traditional stuff, like the traditional statistical model, regression or decision tree, shallow decision tree. But what we are going to talk today is really more sophisticated machine learning, deep network or gradient boosting machine, how to make them as inherently interpretable so that we don't need additional tool like the bottom. So I'm using analogy like cooking. We want the ingredient really, really good, not putting MSG to make it taste good. So that's what we're trying to do with intrinsically interpretable model, which is very, very important in regular industry like banking, particularly when we're dealing with model that impact customer, like approving credit or approve or decline credit. So all those things are very, very important. Then the at least if you ask me, there is no place to do a black box model with post-hoc explainer. Model for highly critical, high impact area need to be inherently interpretable. Can we do it in inherently interpretable without sacrificing performance? And what are the advantages of inherently interpretable that we get beyond using black box and applying explainability? Okay, so that's really the topic here. So black box model with post-hoc explainers. Nowadays, a lot of article out there. People start realizing the problem with all this tool, all this additional or auxiliary tool. As I said, they are simplification. They are not 100% truthful. In particular, when the model is overfit, this explanation can be very misleading. And if you ask me about overfitting in machine learning, all machine learning model overfit. All machine learning, or most, if not all machine learning model overfit. So with that, we start with area that is really problematic to apply post-hoc explainer. Okay, let's look at inherently interpretable model. Unlike post-hoc explainer, we're going to construct model that inherently interpretable. An inherently interpretable model is very important, particularly for the human that it will be in the loop or the human user. Interpretable model facilitates intuitiveness. It's insightful. So when model go wrong, we know what to do. We're not flying blind. And so that's very, very important because every model will be wrong, as I said before. Okay, the inherent interpretability, unfortunately, is a very qualitative concept. And we can talk about qualitative measure instead of quantitative measure. Some of you that were interested in more detail, you can read the paper that we published that I co-author, Designing Inherently Interpretable Machine Learning Model. Okay, so let me talk at the very high level how to design interpretable machine learning model. It has two aspects: the feature itself, the input to the model. So how we construct feature that will facilitate interpretability. The second thing is dealing with the model architecture itself. One in the feature is it need to be meaningful. What is the feature really mean? The features need to be causal. It has cause and effect instead of just correlation. The feature need to be regularized in the sense that we cannot just throw 400, 500, or 1,000 variables, because then you're dealing with correlation instead of causation. You need to regularize it. You need to reduce it. You need to choose the important variable only. So you need to regularize it because the fewer you can, it's more compatible to human mind. People can understand it. So the trick is always how to do that without losing a performance. And then talking about architecture constraint, how can we construct a model with certain architecture, certain design, so that it will be interpretable? A few things that we can look at. The model additive model are very more interpretable because, for example, some of you familiar with regression model, it's additive. You have x1 plus x2 plus x3. So it's additive. So now we just make it more complicated. Instead of x1, I'm going to be complicated function of f1 plus complicated function of f2, and so on and so forth. So make it additive and modular. Sparsity constraint. The model need to be sparse, not too complex. So we're going to give an example later when we talk about controlling sparsity and deep neural networks so that it will be interpretable. You may want to impose monotonicity constraint in the model. In the credit decision, this is very, very critical requirement because the effect need to be monotonic. If you have more, it will be better. If you have less, it will be worse. It will be monotonic like that. So that's kind of monotonicity constraint. And then something that near orthogonal improve the explainability as well, because you can talk about feature 1 and feature 2 and feature 3 somewhat more independent. So that's in general the approach how to design interpretable model. So I'm not going to talk about this, but these are some measures. Some of you that interested in can look at the paper. But there are characteristics that I just talk about how to do that. Now, here's a few examples. Then there are many available out there. So Microsoft has what they call it as explainable boosting machine by Rich Caruana, so or EBM. That's one example of interpretable boosting machine. Jerome Friedman from Stanford create what's called rule fit. Okay, that's also something that interpretable. So I'm going to talk about just one example on the right-hand side that's called GAMI-NAV. Remember about modularity and all those things. So instead of, so in here, we apply deep neural networks, explainable boosting machine applying boosting techniques. Here is using neural network. So I have variable x1 and I feed it into submodule neural network that will create it nonlinear. The output still only the impacted by x1. And then the same thing for other variable, modularize it, every variable. With this structure in statistics is called generalized additive model. So it's additive. So I can see the impact of x1, I can see the impact of x2, etc. Now we can go to higher order interaction. Let's interact x1 and x2 and feed it to a network. Let's x3 and x7 feed it into network. So you control the interaction, control the variable. This way we control the architecture and the model will be inherently interpretable because you can visualize it easily. Single variable, regardless of how complex the model is, you can plot it and you can see it, you can get your intuition. Two variable, you can plot it in 2D, you can see it, you can see how the model works, how you can see how the model combined work together. So that's example of controlling architecture of model. In this case, we call it GAMI, generalized additive model with interaction. So some of you that are interested in, you can read our publication in pattern recognition. Okay, now how about if for deep ReLU networks? Okay, deep neural network. Okay, let's look into this. What is deep ReLU? Deep ReLU is very simple. And I'll say why it's so simple. In deep ReLU, basically, is collection of neuron, collection of unit, and each unit is very simple. It's basically adding, for each unit is adding all the input. If the output by adding those weighted average or some weighted sum, if the value is bigger than such and such, it gets propagated. A linear get propagated. If it's smaller than such and such, it will not get propagated. So the unit in that deep neural network is very simple. In each unit, just say, okay, do a weighted sum. If it's bigger than certain value, pass it to the next unit. If it's not, nothing get passed. So that's how the nonlinearity comes from neural network. It's because it's linear or no value. Okay, so or zero. So with that you can have a lot of unit. You can have deep layer. You will have more complexity of information that you can capture and you can represent. So now, once we do this, let me give an example on this because it's very simple. If I'm putting it a very simple in 2 unit only, so it can be on and off each of these. So on and off with combination of this, I have 4 combination, both of them on, one on, both of them off. So what this first layer basically does is basically partition the region, partition the input space into four region with these 2. And then if you pass it on to the next layer, this is, so I'm using this. So basically what it does is for each region, it gets partitioned even further. So what deep network doing is basically recursive partitioning, doing partition into smaller and smaller. And if you are on, it's linear, get passed on linear, you can trace the activation pattern for each data point. It will generate into linear model. It's just a lot of them in deep learning. because every region will have one unique linear equation. But it's no more than that. Deep neural network, ReLU deep neural network, basically is local linear model. The training algorithm, what is learning, is basically learning how to partition the data best so that locally linear model will work best. So that's why representation of local linear model. So when you train the neural networks, basically it's doing that, and you can see how many regions do I have. You trace it, you can see how many regions do I have, each region, what is the performance. And surprisingly or interestingly enough, most region in neural network only see one sample. So if you say, okay, I have linear equation, I only see one sample, can you trust it? So that's the problem with the with neural network. So here's an example, very, very simple example. I'm going to two-dimensional example, very simple. You can see it, just making a classification, whether class 0 or class 1, yellow or blue here, or purple, class 0 or class 1. So you run neural network. In this case, I'm doing 4 hidden layer, 40 nodes. And doing this classification, this is a measure of classification performance that people use. 93% sounds super, super good. And what's in it? The deep network is partitioned the data here into so many regions. In this case, 530 regions. Okay, and the local linear equation is put it on the right-hand side here in green. So many local linear equation, so many linear equation. And by the way, among 530 regions, 530 equation, 85% only have one sample. This is not uncommon in deep network. And you know, when you have one equation with one sample only, they are not reliable. So you cannot just use neural network, you train it, you're done. So you have to do something. This is a beast, you have to control the beast. If you don't want to have if you want to understand how this model will fail and control the risk. Here is, I'm giving example of post-hoc explainer. Post-hoc explainer, I'm talking about the local explanation. So if I have one point in this example, I pick a point around here on the left, on the left side here in the middle, and want to know how the model make decision whether class 0 or class 1. Yeah, the techniques that people use are two techniques that are very popular. One is called line, the other one is called sharp. Sharp probably is the most popular one today. What happened here? If I pick a point in here, I pick a point, a region, a single point on the left-hand side in the middle, it should be variable 1 only. That's really important to decide whether class 1 or class 0 or class 1. It should be just variable x1. If I pick a point at the bottom, or the top, or the bottom, it should be variable x2 only, the vertical only. That's really important. On the left, it will be variable horizontal only. So what happened? So you apply, in this case, I apply deep sharp, kernel sharp, apply line, and then Alicia is the exact, because remember, I said for every point, I can trace it to get exact local linear equation. So I know exactly what variable are important because I have the regression equation. So the regression equation, I pick one, it should be just variable 1, but the explainability tool that out there can be very, very wrong. So it says variable 1 and variable 2 are important. It's not. For that point, for the decision at that point, is only variable x1 only. So we have picked a few examples here. It's just to illustrate that be careful when using those tools. Okay. I pick another example. Is just before I close it, let me pick another example here to illustrate the importance of controlling complexity of model. So this is, I'm using Taiwan credit data, very popular data, run AutoML. This is the typical things that people do, data processing, drive various algorithm, pick the one of the best. In this example is neural network, just in this example, okay? And then I simplify it, okay? I can simplify it, I can control the complexity. In this case, I use what people call L1 regularization. So when you control complexity, the number of local linear model, the number of region reduced, that's the red color, without reducing the performance or or just slightly reducing. So I regularized it. In this case, I regularized it until I don't need 550 equation. I only need 5 linear equation. The model still perform well. So that's the green point. Okay. And when you do that, actually, when you look at how important a variable, when you don't control it, you come up with some nonsense result, some nonsense effect of variable. All this variable, when you control it, you got the right-hand side. It's the right direction. So this is the danger of using just training machine learning using AutoML. So you test it, it looks good. Remember, when we test it, it's 0.77. Okay, it looks good. When I simplified, the performance declined a little bit, not by much, but the model is correct. The model that performed really well is the model that is incorrect, actually. So that's a lot of problem with machine learning is like that. Here, why is that? Well, people can do hyperparameter optimization. We can have different complexity in the model. So the chart on the top right, it can have different complexity. I'm plotting each point here is a model, okay? They can have different complexity. Going to the right, the measure of complexity is more complex, and the vertical is the performance. So a lot of model with similar performance, but very, very different complexity. And different complexity is basically overfit. So if one choose based on testing data only, it will overfit. So if you apply AutoML, pick the best. What happened when the world changed? Because shift happened in real world. So here's an illustration. If I regularize it, if I don't regularize it, I just simply pick which one is the best. This is AUC, the larger the better. I pick the red one, okay? Because red performs slightly better than green. But when the world shift, the model that is in red degrade very, very, very rapidly. So when you have a machine learning model that require frequent retraining, people talk about frequent retraining in machine learning. It's most of the time it's because of overfitting issue, not controlling the architecture. I think I ran out of time. Let me stop right there.